Hey class, starting out Unit 2 with solving systems. The goal for today is that you can solve a linear system by graphing, substitution, or elimination. We're going to kind of combine them all. And then you can also identify if you have one, many, or no solutions. So first, a system of equations is when you have two or more equations. And we're going to deal with systems of linear equations, so two lines. And then we have three types of solutions. So we have two or more equations, so two or more lines, it makes a system. You have one solution if the lines intersect in one spot. That's one solution. And that solution is a point, an xy value where the lines intersect. You have no solutions. That would be where the lines are parallel. So they never intersect. And then many solutions is the system is the same line. So they intersect at every point. So we have three methods to solving. The first method is to solve by graphing. So remember, we graph the line using our slope-intercept form, mx plus b. So we have our system here. Our first equation has a slope of 1, it's a 1x, and a y-intercept of 5. So to graph that first line, we would start at positive 5 on the y-axis, and then graph it with a slope of 1. That's up 1 to the right 1, or down 1 to the left 1. So that, graphing that line. And then we could graph the next line. This one has a slope of -4, or -4/1, and a y-intercept of 0. So we would start at the origin, and then it's down 4 to the right 1, so negative slope, or up 4 to the left 1. And then we can find where they intersect, which is this point right here, which appears to be -1, 1, 2, 3, 4. -1, 4. So the solution to the system of equations is the point where these lines intersect, and in this case it's the ordered pair -1, 4. So this one was nice to solve by graphing because they're both already set up for y equals mx plus b, y equals mx plus b. So graphing makes sense. We can throw both of these on the graph and find where they intersect. In our next example, you'll see that we have this equation, -4x plus 2y equals -6, is in standard form. And then we have y equals x minus 1, which is in slope-intercept form. This is a perfect problem set up for substitution. Because we have a variable isolated already. For substitution is where we want to substitute in for one of the variables. So you need one of the variables isolated, like a y equals or an x equals, which is what we have. We have a y equals by itself. When I do substitution, I like to write my system kind of next to each other. And then I have the y equals x minus 1. Since this is y equals x minus 1, I'm going to take this x minus 1 and I'm going to substitute it into my other equation for y. So I'm going to plug it in over here for y. So that's going to be -4x plus 2 times, now instead of y, I have x minus 1 equals -6. And then I'm going to solve this side for x. Notice when I make that substitution, I plug in the x minus 1 for y. Now I have an equation with just one variable, x, so now I can solve that. So first thing you're going to have to do is distribute this 2 into the parentheses, so it's going to be -4x plus 2 times x is 2x, 2 times -1 is -2, equals -6. Then combine like terms, -4x plus 2x is -2x, minus 2 equals -6. And then add 2 to both sides. We get -2x equals -4. Divide by -2, and I get x equals 2. but my solution is an ordered pair where these lines intersect. So right now I have the first coordinate, the x coordinate is 2. I still need to solve for the y coordinate. So then I bring it back in and I substitute it into the other equation, which was y equals x minus 1. Well, if x is 2, y equals 2 minus 1. That means y equals 1. So your y coordinate is 1. So the ordered pair where these lines intersect is 2, 1. I like to set it side by side so that I know I have to do work in both columns until I'm done. So I do the work here and then I do the work here as well when I substitute it back in. So we can do that one more time. Find the solution to this system. I'm going to solve it using substitution again because it is y equals. So I have a nice isolated variable. I can take that y and plug it right back into this y. So I'm going to set it up as 3x minus y equals 17. And then I have y equals negative 2x plus 8. I'm going to take the negative 2x plus 8 and put it into the equation for y. That's going to be 3x minus, put in parentheses, negative 2x plus 8 equals 17. And then you have to distribute. This negative here is like you have a negative 1. So you need to distribute that negative 1 into both. So you have to subtract both pieces, not just the first piece. So you get 3x, negative 1 times negative 2x is positive 2x, and then negative 1 times 8 is negative 8. Or you can think of it as you're subtracting negative 2x, which is adding, and then you're subtracting the 8. Then combine like terms, so 5x minus 8 equals 17. Then finish solving for x. So add 8 to both sides. 5x equals 25. Divide by 5. We get x equals 5. I still need to plug that back in then over here to get my y coordinate. So it's negative 2x plus 8, where x is 5. So negative 2 times 5 is negative 10. Negative 10 plus 8 is negative 2. So there's my x coordinate, my y coordinate. My final answer for this one would be 5, negative 2, the ordered pair where they intersect. That's the solution to the system. All right. Notice how this one is set up. They are both in standard form. We have an x plus a y equals a constant. X plus a y equals a constant. So this one's set up perfect for elimination. So if they're both in standard form, the best method is to use elimination unless it's easy to solve for x and y. But in this case, it's a 5x, 6y, or 3x and a 6y, so it's not necessarily easy to isolate the variable x or y. So I'm going to use elimination. When you're solving with elimination, you must have opposites. And this one's set up perfect because I have a negative 6y and a positive 6y. And that's what you need with elimination, because once you have the opposites, then you add the two equations together. So you get 5x plus 3x is 8x. Negative 6y plus 6y is 0. So now the y is eliminated. And then 48 and negative 32. So the same thing as 48 minus 32, so 16. And now you're just left with an x, so you can solve for x by taking and dividing by 8 on both sides, and you get x equals 2. But just like the last one, that is only our first coordinate to our solution, so we do need to solve for y. When you go back to solve for y for elimination, you can use either equation to plug it back in. And technically for substitution, you can use either equation to plug it back in as well. But the one that's already y equals is easy to plug back into. This one, choose whichever one you would like. I'd prefer to work without negative, so I'm going to choose the 3x plus 6y equals 48. And I'm going to plug in 2 for x. So that's going to be 3 times 2 plus 6y equals 48. So that's 6 plus 6y equals 48. Subtract 6 from both sides. And I get 6y equals 42. Divide by 6, and y would equal 7. So my final answer would be the ordered pair 2, 7. You could check this answer by plugging it, the 2 and 7, into the x and y, into both of these equations, and you should get, in the top one you get negative 32 equals negative 32, and the bottom you should get 48 equals 48. So when you plug this back in, it should make both the equations true. That's one way to check your answer. So this one is set up for elimination as well. We have standard form x plus y equals some constant, x plus y equals some constant. However, I don't have opposites yet, so you need to make one of them opposites. So I'm going to make the top equation an opposite. You can choose either the x or the y. If I wanted to eliminate the x's, I would need a negative 12 in top. So I have a positive 4, I need a negative 12, so I'm going to multiply the whole equation by negative 3. So rewriting this, negative 3 times 4x would be negative 12x. Then negative 3 times 5y would be negative 15y. And don't forget to multiply everything, so both sides. 12 times negative 3 would be negative 36. Then I'm going to keep the bottom equation the same. Sometimes you have to multiply both the top and the bottom by something in order to make the equations be opposites in the x or the y. But as long as you multiply everything in the equation, so all parts, then you're not changing the value of the equation. You're just increasing the coefficients by the same multiple. So then we have 12x plus 15y equals 36. For my second equation, didn't change. Now I add them together. Negative 12x plus 12x is 0. Negative 15y plus 15y is 0. Negative 36 plus 36 is 0. So in this case, I get a special situation where I get 0 equals 0. If 0 equals 0, and you could go back and look at these equations, and you might notice that they're almost the same except for a multiple of 3. So if you get 0 equals 0 algebraically, that means that these lines are the same line. They have the same slope, the same y-intercept, which means they will intersect at all points. So this is an infinitely many solutions problem. When solving, or when graphing, these would be parallel lines. When solving, if you get 0 equals 0, it's many solutions. Let's say you would have came down and you would have gotten like the x and y cancel, so you get 0, but then you get equals 5. Well, that would be a case when you're solving and you get 0 equals 5. That would be a case where you get no solution. So these would be the parallel lines. I'm sorry, many solutions is the same line. And no solutions would be parallel lines. And algebraically, you would get something like 0 equals 5 when you're solving. Okay, the initial cost for Travis and his band to record their first CD was $15,000. Each CD costs $4 to produce. If they sell CDs for $10 each, how many must they sell before they make a profit? So we have the two equations here. It looks like our first one was each CD costs $4 to produce, and then they had the initial cost was $1,500. So the cost for CDs was the y equals $4 per CD plus the $1,500 for the initial cost, because slope is the rate of change and y is your starting value or your initial cost. And then the income is that they're going to get $10 for each CD. So the equation for the income of CDs is $10 per CD.
What are you doing now?
You can see this graphed over here to the right, and it says, what does the point 250, 2500 mean? So that is right here where these two equations intersect. That's where the cost for the CDs and the income of the CDs intersect. So that is where essentially their break-even point is. So their cost and their income meet at 250 CDs, and that's $2,500. So that's kind of their break-even point. Where the equations are equal. So how many must they sell before they make a profit? Well, at 250 CDs, they're equal with their cost. So in order to make a profit, they have to sell any more CDs greater than 250. So they would start making profit at CD number 251, because you can see their profit equation then would be slightly higher than their cost equation past that point. All right, that's all I got for you. I have videos of graphing, videos of substitution, and videos of elimination, all done separately. So if there's one particular method you would like to see more practice with, I would search my YouTube channel for, solving by substitution, solving by elimination, or solving by graphing to find those individual videos. Have a great night.